Hi and welcome. My name is Tom Laus. I'm a freelance data engineer contracted at Shell, Rotterdam, the Netherlands at the moment, and I'll be talking to you about deploying Apache Spark jobs on Kubernetes with Helm and Spark Operator. It's quite a mouthful, but I will explain to you how I stopped worrying about deployments and increase my productivity. So why do we even want to run these Spark jobs on Kubernetes in the first place? There's good alternatives already baked into the Spark ecosystem. The most common one is running it on top of a Hadoop cluster with Yarn. And you can also run standalone or even use one of the cloud solutions like Databricks or Amazon EMR or something. Why do we even want to run it? It actually seems like a pretty bad idea to begin with, right? Because it's not a ready to deploy platform. You have to develop a lot of scripting, a lot of configuration, additional modules. You need image registries, operators. And there's a lot of more DevOps involved than just running your Spark jobs on a normal cluster. So before I answer that question, let's take a step back. As a data engineer, I'm really focused on building data solutions, data-driven solutions using the Spark ecosystem. I want to run, my main focus is building these sometimes simple ETL jobs and sometimes more advanced machine learning jobs. But when I have created this finely crafted piece of software, I really don't care a lot about where I run it. I just want it to run predictable and run in a scheduled fashion. And if I want to look at the results or the logs, I just want to be able to do it. So I don't really care about the ecosystem that much. But there is a problem with that, because there is a challenge in all these ecosystems, because you have to be aware of what is the Spark, underlying Spark version that is currently available in the system. Are we running Spark 2.4.0 or 4.5 or even 3.0 or maybe an old one like 1.6? These are all things you have to take into account. Also, maybe other libraries. What is the Hadoop version? Can we run Scala? Can we run Python? And even if you have decided on the base platform versioning, this will change continuously because there's a team upgrading and updating these platforms to a newer version continuously. Also, you have to take into account how do you want to run these Spark jobs, because just to run something on Hadoop, you need maybe some bash script to run your Spark submit, and you have to inject that with secrets and keys and locations, and where do you even store the jar file, and all these pieces reduce your very stable and very finely crafted piece of software into a big pile of technical debt. So is there a solution? Is there a solution for this? Well, yes, there are ready-to-go platforms, and I think Databricks Delta is one of those solutions you could use. And there's other solutions you could use out of the box that have all these components nicely packed and all these schedulers for you. But it wouldn't be nice if there was a way to just bundle all your dependencies and configuration into one system and just deploy it on the go? Well, yes, of course, it's Kubernetes, and in quote-unquote ordinary software development, this is already widely spread and widely used. It's a very good way to pack all your dependencies into small images and deploy them on your Kubernetes cluster. So are we just late to the party with data engineers? Yes and no. It's one thing to just deploy some microservices, but a whole another thing to deploy a distributed processing engine on Kubernetes. There's a lot of configuration involved and a lot of things you have to take into account, like how do I deploy my executors, and how do I communicate between my executors, and how big are going to be my executors going to be, how many CPUs, how much memory. So there's a lot of things you have to configure to make this work. And instead of explaining to you how you can do this, I want to show you this in the demo. So to deploy our Spark jobs in a demo, we're going to need a Kubernetes cluster. And for this purpose, I'm going to use Minikube. It's just an ordinary Kubernetes cluster, and a nice thing, it runs on your local machine. So it's nice to try this out yourself. Now we're actually going to create our Kubernetes cluster. We use the minikube start command to start the minikube cluster. We use the kube admin bootstrap parameter, and we give it a bit more CPU and memory than default because we actually want to run a Spark job on our Kubernetes cluster, and we want to please the JVM. Another interesting part is the insecure registries subcommand, which actually allows us to push and pull images from the minikube registry for our use in the Kubernetes cluster. The only thing we still have to do is enable this. So when it's done, we'll implement the add-on. And yep, here we go. And we enable the registry, and we can actually see if everything is up and running. And we see our Kubernetes is up and running, and we're ready to go. So now we've seen how we set up our basic Kubernetes cluster, and now we actually want to build a data solution. So I'm going to show you how to build like a basic Spark solution. It's not the interesting part of this talk at all, but it will be running on the Kubernetes cluster in a short while. Come to the least interesting part of this presentation is the application itself. We just want to have an application that is running some busy work, so we can actually see the Spark cluster in progress. For this, I'm using the Movie Lens 20 million record data set. It's movies like Toy Story, Jumanji, and ratings for each of the movies. And what we're actually going to do is, in this basic Spark job, we're going to create a Spark session. We define an input path where to read the movie files from, and an output path for the target Parquet file that we're going to generate the average ratings. Read the movie data set from the movies.csv. We're going to read the rating data set from ratings.csv, and then we're going to do a join, a broadcast, a group by, aggregation, and some repartitioning to really make Spark run on its tiny cluster. In the end, we'll just do a count and also write all the data into a Parquet file where we get the average rating for each movie. So to actually run this job, we actually need to define our build.spt, and we are going to run it on Spark version 2.4.5, and we don't need a lot of dependencies. The only dependencies is Spark Core and Spark SQL. And as you see, we say provided, because we're not going to bundle all the Spark libraries in this project. We're going to actually use an external base image where we're going to put our fat jar in. So going to that immediately, I decided to put the base image also in this repository, but normally you would store it outside. We have this Docker file, and just to speed up the process, we're going to immediately create this Docker, because it will take some time, and I'll go over it with you. So for this Docker image, we're going to use the basic image from the Spark operator. You can use any image, but the nice thing about the Spark operator is it comes pre-installed with some scripts that make it easy for the Spark operator to deploy your Spark jobs. So that's a good base to start. But actually, I'm wanting to not just use the Spark 2.11, but the Scala 2.11 libraries, but the Scala 2.12 libraries. And for example, I wanted to use the Hadoop version 3.2 instead of the bundled Hadoop 2.7. So this gives you flexibility to install and configure all the dependencies you want in your base image, and you can reuse this base image for other jobs as well. So another interesting part is you can actually also configure your Prometheus out of the box, and there is this little bug currently in the Kubernetes client that you can install this additional jars to patch it, but in a future version you can just remove this, and your older jobs keep running on the older version of this Docker image, and your newer versions can run on newer versions. In the end, the enter point is called, which can be used by the Spark operator, but we'll get to that. As you can see, in the meantime, we actually, the script I called, it's nothing fancy, it's just some information about building this Docker image, which is happening in background, and in the end it gets pushed to the registry, which in our case is the Minikube registry. So in the end of this, we should see that this Spark runner of ours, the 0.1 version, is now available in the Kubernetes registry. So that's great. So we have our base image, we have our application, and now we just have to build our application and put it in that base image. And you can actually do that also in SBT, because you can use the Docker plugin in SBT. It's SBT Docker, and when you have that, you can actually configure your entire Docker image how you want. You can say what the name should be and how it should, other information, but the most important part is defining your Docker file. And in our case, it's pretty easy, straightforward, because we're just going to use this Spark runner base image, and we're going to add our artifact. And what is our artifact? It's actually our fat jar that we can build from this code. So in our case, there's not going to be a lot of external libraries, because these are marked as provided and there is no other libraries. But you could, for instance, add Postgres libraries into this fat jar, or some other third-party libraries that are not going to be part of your base image. So running this, I'm going to also create a Spark image, and I'll show you what's happening in this script. It actually does nothing more than just calling SBT Docker, but it will pass the image registry information from the Minikube, so it pushes to the right version, and it will tag it based on the version that is available in SBT, and push this immediately. So it's normally you would see the scripts as part of your CI/CD pipeline, but for now we're gonna run this from this small bash script for the Minikube. You see it's pretty fast. The compilation happened pretty fast, and now it's pushing, and in the end you see that our image is now also available in the Kubernetes industry. No, this is the intro to the last piece of the demo. Well, for us to actually deploy these images on the Kubernetes cluster, we need a way to deploy them as idiomatic and easy as any other workload in Kubernetes. And for that, people have created the Spark operator. So we're going to install the Spark operator right now. But before we can do that, we have to create some namespaces. And the first one we're going to create is the Spark operator namespace, where the Spark operator is going to live. And the other one is going to be Spark apps, where we can actually deploy our Spark workloads. The reason we keep these separated, because we're going to give the Spark operator some elevated privileges to create and destroy pods in the Spark apps namespace. Technically, it's not necessary, but it's a best practice, I would say. So we're going to create a service account. Well, called Spark, so it's not very original, and we're going to give these service accounts some elevated privileges using the cluster role, and we call this the Spark operator role. We give it added privileges in the namespace of Spark operator. So the roles have been created. So the next step is actually to install the Spark operator in the Spark operator namespace. For this we need the incubator repo, and because it's not yet released as mainstream, so well, we have to update to get the latest version. Well, we already had them apparently, and now we can actually install the Spark operator. We give the name Spark, again, not very interesting. But we use skipper CRDs. I think there was a bug in the version. I don't know if it still persists, but it still works. We installed in the Spark operator namespace, and we enable webhooks so we can connect with the Spark operator from outside, and we make sure that the Spark operator will deploy all its applications in the Spark apps namespace. The log level is just for debug purposes. We should be seeing the Spark and it's already done. So you see the webhook for the Spark operator in it has completed, and the Spark operator is now up and running. So now we have to switch to actually deploying. So build a Spark application deployments. For this we need Helm chart. Well, that's the easiest way at least. So the most important thing is that you want to deploy the Spark application. The moment you deploy this in Kubernetes, the Spark operator will trigger and deploy the cluster based on the specification you provide here. As you can see, there's a lot of conditional logic here, and the reason is that we keep this template as generic as possible, where the values are filled by the information that is present in the chart and values files that are combined into one Helm chart. So for going back, you can see we hard-coded the type to Scala, for instance, but if you specify pool policies or pool secrets, or even the main class or the application file, it will get picked up and rendered into the template. And the Spark operator recognizes these specs and uses them to deploy the cluster. And also important is for the driver, how many cores does it have, how much memory, and also for the executors. And of course, which image is going to be used. So a lot of information for this comes from 2 different files, but actually in our case 3 different files. So we start with the chart. The chart is actually some meta information. We just give the name, we give the version, some description, and the values gives you a more detailed configuration for which Spark version to use, which image to use, where is the jar located in the base image, and which main class should be run. But as you can see, a lot of this information already exists within our project because these are all configuration files we define in our build.svt. And if you noticed, you see that these files are actually generated by the build.svt. So if we go into this one, you see I created this small function that actually does nothing more than creating these 2 files, as you can see them, based on the information that's already present. And the advantage is because we call this function every time you do a Docker image, it will render the correct chart and the correct values based on the current image. So you don't have to keep track of that you update the same version in both your chart and your SBT, and the main class name is still the correct one, and the jar is in the right location, because these are actually coming from the SBT that generates them. So that's a pretty good advantage, but the only thing we haven't defined in these auto-generate files is how to run it, how many CPUs, how many memories. And this is the interesting part. We actually created a values-minikube where we can actually, for this specific environment, we can configure this. So you can see we define that our image registry is localhost port 5000, which is our minikube registry. We use this Spark service account, which we just created, and we point to some volumes that we still have to mount, but these are very specific to my minikube environment. Also, not a lot of cores or memory for this Spark job because it's just a small cluster. But you can imagine that for a production environment or a cloud environment, you would increase this value and have the arguments come from some Kubernetes secrets and have an outside image registry. So you can, in theory, define all these values for each environment and have the CI/CD pipeline bundle the correct environment with the right values and have your chart repository chart ready. So this is pretty cool. So these values are generated. This value you just manually enter, but now we have this Helm repository. But how do we create the deployment out of this? We can do Helm package and store it somewhere, but actually you want to have a Helm repository, a Helm registry, so to say, where you can push these to. Some image registries offer these out of the box. I know for a fact that Azure ACR actually both has the power to store normal images, but also Helm charts. Unfortunately, the image registry in Minikube doesn't, so we actually need to run a basic Helm chart museum, and that's pretty cool because that's actually a normal, it's a Docker image that you can just run, and it actually has some API endpoints to retrieve your chart and some API endpoints to push your chart. So it's fairly straightforward. I just have to make sure that we are using the Minikube environment, and we can just do Docker run. And this will download this version of the chart museum. I think this is the latest, and call it chart museum on port 8080. And I'm storing it locally, but you should do something more permanent when you actually deploy something like this, or use outside image registry. And we can actually see that at the moment we have this chart registry running with no entries. So the final step has come. We have Dockerized our image, and our next step in the CI/CD pipeline will be then to bundle this. Yeah, so we're going to publish the chart, and I'll show you what's happening in the background. Well, that's pretty quick. So if we run this command again, you see the chart has been uploaded. What actually happens, it's pretty okay. So what we said before is actually we combine these Minikube values with the values. There's no good way to do this using Helm commands at the moment, so this is some makeshift code to make it happen. But in the end, it's just nothing more than add this chart museum repo and push this data, push this combined chart of the Minikube to the chart museum. And you can imagine if you run this in a CI/CD pipeline, you would, based on the environment, use the different values and push them to the correct chart museum. So we can actually do now on Helm repo list. I think chart museum should be part of it right now. So if you do Helm repo update, we should have all the, we should be able to deploy. So now we have all our components in the Kubernetes cluster. We have our images in the image registry. We have our charts in the charts museum. And now we just want to deploy our application. And this is what I'm going to show you next. But before we deploy, we have to do one more thing. As you might remember, is that we have these two mount points, input data and output data, that are not pointing to anything right now. What would be useful is actually to use a Minikube mount command to point the local dataset ML20 file directory to input data, and I'll use the ampersand to keep it active in the background. And Minikube mounts to some local Parquet file for the output data. So I think should be empty right now, but in the end there should be some data here present. So Helm charters are updated, the images are updated, so the only thing that we just have to do is install this Helm chart. I'm going to use the upgrade command because it will keep me to run this command continuously every time I have a new version. We go at the movie transform. I'm going to use the latest graphic transform movie ratings. I'm going to run it in Spark Apps and I'm going to install it. So it's installing right now. So we should be able to see something happening. Oh, so it's already running. So normally it starts the driver first, and that will trigger the executors to be get created. So as you see, that's pretty fast. So what's happening in the background? We can do some port forwarding to see what's going on using Spark UI. And you can see this is Spark job running on top of our Kubernetes cluster, so that's pretty awesome. It's doing the count at the moment. If we look at the executors, you actually see the two, this is the driver that will start with the two executors, and the driver is actually not doing anything, of course, and the executors have one active task at the moment. As you can remember, the executors only have 1 gig of memory and 1 CPU core, so they're not doing something fast. So you can see the count, and so here you can see the movie database, like almost 30,000 records getting loaded, and the 20 million reviews to get broadcasters, joins, some aggregation, and in the end it will get stored. See what the progress is on our application. You can still running, probably almost done by now. So we should be getting some data in okay. Yeah, you see, oh, it's already done. So check again. Yeah, it's completed. We can actually inspect always the logs of the driver if we want to. And you can actually, there's a lot of debug stuff from the entry points of our base image. But here actually our Spark submit actually starts. And here's the first output starting in Spark UI. Writing 20,644 records. Oh, double slash, and it's done, and it starts Spark Web UI. So this is pretty cool. So actually see if it worked as expected. We can do Parquet tools. We see do a row count on this movie ratings, and we should get, well, you see 26,744 as expected, and we can actually look at some of the ratings, and you see some movie has an average rating of 2.5 based on 2 ratings, and Hope Springs has average rating of 3.25. 136 rating. So this is not the interesting part, of course, but you see it's we actually deployed a Spark job on Kubernetes right now. So that is pretty cool. Success, everything works as expected, so that's pretty cool. It seemed like a lot of work to begin with, but at the end we created a very easy, robust way to deploy our Spark jobs using Helm charts. And you can imagine that the moment we have this all in place and up and running and a correct CI/CD pipeline, it will be very easy to just make minor changes to your environment, change your base libraries, change your versioning, and just deploy new versions of your Spark application without even having to worry what the underlying platform is. Now we've seen how to deploy this. We've deployed it manually. So what are the next steps? You could imagine building a scheduler on top of this. We could use Kubernetes scheduler or Airflow or some other way to deploy these jobs in a timely fashion. Actually, you can run Airflow pretty nicely on Kubernetes as well, which we are doing at Shell. You can also think about upgrading your Kubernetes system to use auto-scaling clustering node pools, so you can actually scale up your clusters pretty big and scale them down when the resources are not needed. And there's a lot of other things you can do to improve these Spark jobs in this way. We haven't even touched monitoring or logging or alerting, but it's all minor steps from when you have this deployed and ready. Here's some links about the things I talked about. There's links to Spark operator, Helm. Some of the code that is being used in the demo is already available on GitHub. You can read it and use it and try it yourself. Are there any questions?